Welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the basic principles of mechanics and in particular on how to deal with the equilibrium of forces. Newton's first law says that a body moves with constant velocity in a line or remains at rest if there's no resultant force. That law is the context for problems which are called statics, where there's no motion and in particular no acceleration. And that has to mean that the vector sum of the forces is zero. And it's problems which focus on that which we're going to consider here. Now, we've dealt with force resolution in the previous video. This is a reminder. And the slide is exactly the same as the one of the previous video. It makes the comment that the second is easier to apply. The point being that if you choose your directions of resolutions carefully, your problem is made much easier to solve. Let's look at the first example where we've got a system of forces. We've got a P newtons and a Q newtons acting, and we've got to try and find out what P and Q are. And what we know, because it's in equilibrium, is that the vector sum of those forces is zero. Well, that means to say that we can use principles we can resolve. And in particular, if we resolve if we resolve vertically and horizontally, then as I remarked in the previous video, you end up with easy equations for P and Q. If you resolve in any other directions, you'll end up with a mixture of P and Q in each equation, and that makes it more complicated to solve. So we'll resolve horizontally and work around the diagram with each of the forces. So I'll start with the 10. We've got 10 cos 50 horizontally to the right. I'll take to the right as positive. We've got, moving counterclockwise around the diagram, we've got a Q to the left, so minus Q. Then we get to a P, but that's vertical, so there's no contribution. And then finally we get to the 7. It's probably easier to think of the 20 degrees that's missing there and get 7 cos 20. Or you could say sine 70, it's the same thing. And that must be equal to 0. Now, that's pretty well done it, because Q can be made the subject of that and a bit of arithmetic with the calculator, and we've got the answer. Now, similarly, if we resolve vertically, following exactly the same procedure, we start with the 10. Well, that will be 10 sine 50, or you could say 10 cos 40 if you prefer. It's the same thing. There'll be no contribution from Q. We're taking upwards as positive, so when we come to P, it's negative. And then also the component of 7 will be negative. We'll have minus 7 cos 70. Or if you really wanted to be perverse, you could say 7 sine 20. It would be the same thing. That must be equal to 0 because we're in equilibrium, and that gives us an equation which we can solve for P. So here are my two equations that I started with, the first one and the second one. And in each case they've been rearranged to make the unknown the subject. That's easy enough to do. And then the use of the calculator. Note again that I've put my full display in, or at least abbreviated, and then rounded it. And similarly, this one can be rearranged to get P equals just by adding P to both sides. And so we again we get some numbers for the calculator giving a display, and so my final answer is that P is 5.27 to 3 significant figures. Now again, if you look at the question and the last lines of the answer, there's actually two of them here. Each of them makes perfect sense in the context of the question that's asked. There's no newtons here because the force is P newtons, and P, for example, is 5.27. So the newtons are implicit rather than explicit in this problem. Now let's look at a more complicated one, reminiscent perhaps of the one we looked at in the last video, with a box on a slope with a 10-degree inclination. The first reaction is always to draw a force diagram, and again I say that I draw a gap between the box and the floor so that I'm clear what the box's particular forces are. So in the steps for a diagram, we'll have three forces. We have the normal reaction from the surface. We have the friction upwards because it's on a slope and will be inclined to move downwards, and we've got the 6g to represent the weight. I haven't put any newtons on the diagram because everything's in newtons, so it just would make it more complicated. Now this time we're trying to find the reaction and the friction force. If you were to resolve horizontally, say, that equation would involve a component of F and a component of R. To remember the 10 degrees there. And if you resolved vertically, the same would be true. So you'd end up with two simultaneous equations in F and R with complicated numbers. It's much easier to use the flexibility to choose your own direction. And in this case, if we choose parallel to the slope, R won't figure. And if we choose perpendicular to the slope, F won't figure. Both those two equations will then be easy to solve. So if we resolve parallel to the slope, it says using Newton 2. In a way that's a bit pedantic. It's correct, but it's a bit pedantic because in Newton 2 there's an acceleration, and here we're saying the acceleration is 0. So we've got an F up the slope, and that is the only other contributory force up the slope is the component of 6g. F doesn't figure. So we've got F minus 6g, and it will be sine 10, because again, with a bit of thought, we can see that this angle, this will be 80, and this one will be 10. And that equals 0. Another way of looking at it, which would be equivalent, would be to say, because you've got no acceleration complicating the situation, you could balance forces to the right up the slope against forces to the left. If you did it that way, you'd just get F equals 6g sine 10. Resolving vertically, we're going to get nothing from the F, but we're going to get a whole lot from the R. We'll take positive in the R direction, and then we're going to have a contribution from the 6g cos 10. So those two equations will rearrange to F equals and R equals very easily, and that will give us the answer. So let's look on the next slide, and that should be there. Yes, so we've rearranged the first equation as F equals 6g sine 10, and the usual routine, put in g as 9.8, put in the full display, and round it. So the frictional force, conclusion, is 10.2 newtons. Now using the second equation, nothing new there, that's what I got on the previous page, rearrange it, put the numbers in, and we end up with an answer 57.9 newtons for the answer. Notice in this case, since we're asked for the frictional force, there must be newtons in the answer, and similarly for the normal reaction. But in the intermediate part of the question, I didn't have any reference to newtons because the units were all, well, they were all newtons in fact, but the key point is that they should be consistent. Right, now we've got a string problem. We've got an 8 kilogram mass hanging from two light strings. We're to find the tension in each string. Well, the tension presupposes that we've started to think about forces, but anyway, the first step should be a force diagram. So what forces will there be? The tensions in the string, obviously. The only other force will be the weight of the bob. So if we put those forces in, given the angles given in the question, we end up with that configuration. And so again, the question is not what do we do, because it's obviously resolved, but what direction. And because these two strings are conveniently at 90 degrees one from the other, then it makes sense to resolve parallel to each of them in turn. So if you resolve parallel to T1, you won't involve T2, you will involve the 8G. So you'll get T1 is equal to, let's do it left and right this time, or rather up T1 and down T1. If we do that, we get T1 is 8G times cos 25. If you did it as F equals ma, then it will be T1 minus 8g cos 25 is equal to 0. It's equivalent. And similarly, if we resolve along T2, that will give us T2 is equal to 8g sine 25. In each case, the drill is to draw the force diagram and then go right round it, ticking off every force to see what its contribution is to the equation. The fact that we've chosen the directions to eliminate two of them makes it simpler, but it shouldn't allow us to cut short that mental step. That's what we're doing. So there we are, our two equations. Look, in this case it was done as F equals ma again. It's equivalent. I simply got this equation in one step rather than two. So we get our two resolutions, we put the numbers in, and again correcting, we end up with numbers 71 and 33. Again, notice I put the full display in case I need to come back to it for a supplementary answer. And then finally a sentence which answers the question in context with the units. If you did it by an alternative method, it's worth considering. What you could do is say you've got three forces in equilibrium, which means to say you must have a vector triangle. Now what would that vector triangle look like? Well, you'd have a vertical force downwards. That's supposed to be vertical, however vague and approximate it looks, 8g downwards, and then you would have, you remember on a triangle of forces, your forces must follow each other round, so this would have to be the T2, so you've got a T2 like that, and then finally the T1, which is at right angles to it, would come in over here, so that's a right angle. The limitations of my handwriting in this medium are very apparent here. Now the only thing that's missing is the angles, the other two angles. Now, if you look hard at the diagram, this line here is essentially the line of T1, and it's at 25 degrees to the 8g, so that will be 25 degrees, so hence clearly this must be 65. Now at that point then you could use I wouldn't use the sine rule because you've got a right angle, but you could use elementary trigonometry. You would end up saying that T1 cos 25 is equal to 8g. T1 cos 25, or rather, sorry, I've got that the wrong way around, haven't I? 8g cos 25 is equal to T1. That's what would be the analysis of that triangle. And if I go back to the previous slide, not two slides but one, there we are. T1 is 8g cos 25 figures on this line here. So that would be an alternative approach because you've got three forces only. The virtue of resolution is that in situations such as the one with the box on the slope, where you've got more than three forces, it then becomes significantly easier to use resolution. But you've got that technique up your sleeve, the triangle of forces, if you choose to use it for three forces. Well, that brings us to the end of this video presentation. The next in this same series will be on a new topic. So I hope to be with you later to explore that.